What's up, y'all? I'm back with another video, a homebrewed show, at least to start. Check this out. So, I had a neighbor. I'm on a Facebook community Facebook group, and people post all kinds of things in there. And someone had asked if does anybody repair vintage electronics, and I was just kind of following this thread, and it was for this old mixer, um, seeing if somebody could fix it. And I said I would take a look at it. I mean, more and not in a professional capacity because I don't work on audio gear like this. I mean, I repair some of my own stuff. I'm a musician, by the way, for those that don't know, but this is not something I work on routinely. And I said I would take a look at it and didn't promise anything. But this is a Dynacord Eminent 2000 mixer with tape delay, and I think it's from possibly the 70s. Um, but I mean, look at this thing. This is incredible. The owner bought it or was gifted to him. I forget, in a non-working state. But the previous owner said that it's blowing some of the power transistors. That's really all that I have to go off of. But I mean, look at this thing. It's in excellent shape. We were missing one of the fader uh, switches there, or knobs. Um, but I mean, this is just incredible. You got an equalizer here, the settings for the tape delay. I mean, and then of course, there's the magnetic heads. There's the motor to drive the tape. I mean, that looks in good shape. I'm not gonna mess with that. I don't have any experience really working on that. Hopefully that works if we can get it up and running. But I mean, this is just incredible. So you've got 8 channels, 8 inputs. Let's flip this guy around. Yeah, so it's the back of the unit. Again, there you go. Got the serial number 13784. You have the ability to switch between, 110, 130, 220, 240. There's your fuse, speaker connection, specs, and there you go. There's your 8 inputs, got your outputs. I mean, you even got an echo foot switch. That's super cool. But yeah, I mean, this is just, what a piece of gear. Okay, so I just removed this top panel right there. It was covering all this guy up, and it does expose some of the circuitry. Look at that size of that transformer. And this is definitely the amplifier right here. You can see this huge heatsink, massive heatsink where all the power transistors are, in contact with. And that guy down there, that green thing, might be one of the adjustments, and this one as well with this wheel, either to both of these, not sure which yet, being the offset and bias adjustments. That wheel likely being the offset adjustment. And this is the power supply to provide those negative and positive rails for the amplifier. I mean, look, and these big gold capacitors are the large filter caps, and then they do have these additional fuses right here, and they don't appear, just from visual inspection, to be blown. So Yeah, and not quite sure what this board is. It might be the other power supply for the other rails. Um, but I think what I'd like to do is remove this back panel with the large heatsink off so we can get a little bit further in there. Definitely don't want to power it on yet, knowing that may have some blown components in it. I'd like to isolate the power supply first before doing that. I forgot to mention, someone's definitely been in here. You can see there are screws missing for this board. Sorry, my camera's not focusing. And it also looks like this thing took a bit of some, maybe it was dropped or something. You can see it definitely took on some damage on the side there. Yeah. Hey, Snow. How's it going, bud? It smells funky, right? It smells like vintage electronics, huh? Well, we're in the thick of it now. So I've clearly removed the back panel and the uh, tape delay section. And, it looks like somebody really dropped this dropped this thing. It took a pretty hard beating. It's all case is cracked. And then also you've got this crack that runs down this front board. You can see, and it cuts through some traces. It clearly cuts clean through a couple of them. So, all right. So this is the service manual for the Eminent 100A, which is not the same model we have. This is the 200A. I think the main difference being that this one has only 6 inputs, whereas ours has 8, and probably provides a little bit less power, which we'll see in the schematics. And so you can see they've got some detail of the unit taken apart, and then it's all in German. This is a German-made mixer. And so this is like, you can see, they're probably talking about setting the magnetic tape delay, troubleshooting tips for that, specs. Yeah. So I've translated some of this, mainly the amplifier section, the bias adjust, and the um, DC offset adjust. And we'll see that in a bit. Let's just kind of scroll through here. So this is the monitor amplifier. And this is the amplifier, main amplifier. So you got some specs here. Effective power, max 880 watts for a sine wave. And then this is for music, 115 watts. Again, this is probably less than what ours can do, but... And then here is the bias adjusts. And so basically they're doing this using an oscilloscope, and so you're basically adjusting until your crossover distortion has disappeared. Okay, so just at that point. All right, and now we get to the schematics, which are of much better quality here. And so we can look, this is this is one of the input boards for channel 1. So you have your input here, you've got your volume fader here, bass, treble, pots, echo, send. This moves on to the master volume board with master bass, master treble. And then finally, we get on to the area where we're going to be focusing, which is the amplifier. All right, and so this is where it gets inputted. And you can see here they're using this differential amplifier to set the DC offset. This is your DC offset adjust here. This is your bias network, so they're using a transistor as an adjustable diode to adjust the VBE multiplier basically. And this is an AB class amplifier. You got these push-pull transistors and then your power transistors here. Now the difference between this one and ours is you have an additional power transistor on each end. These are in parallel. You've got your ballast emitter resistors here to kind of help to regulate the current, stabilize it through each transistor in parallel. It's your preamp section, and here you've got your two current sources, one for your bias adjust and then another for the differential amplifier. Okay, so yeah, so this is really what we're going to be focusing on, is why these transistors are blowing. Okay, this is the power supply. So this power supply is feeding the power amplifier. It's a center tapped, bridge rectified, yeah, providing roughly 36 volts plus or minus unregulated. And then you have a regulated supply here that's going to providing voltage to other circuitry on the unit. You've got your power for your motor here. Okay, this I believe is, you got your echo, your tape delay controls, and then you have this board here, which is a this is for the monitor. This is the monitor amplifier, which is getting full wave rectified from this guy. When you're full wave rectification with a center tap is only going to provide you half the voltage as a bridge rectifier. But we are getting 35 volts here on the positive rail. And it looks like this, again, is another AB amplifier. And they're using these Zicli, I believe, is how you say it. Kind of like a Darlington pair. But these had the added advantage of, with the Darlington pair, you have two VBE drops, whereas here you only have one. So, yeah, it's basically the product, the beta of these, the product of these two betas equals the total beta for this pair of transistors. So you've got obviously some advantages there for gain. And then it does look like they are bootstrapping this. Here's your bootstrap capacitor, it looks like, to make the impedance look larger, input impedance look larger at your signal frequencies of interest. So there doesn't appear to be a bias adjust for this guy, but it does look like there is a DC offset adjust. So yeah. And then of course you've got, this is all of the circuitry for the driving the magnetic tape delay, which I'm hoping we won't have to get into too much, and that this will just work once we get the amplifier up and running. That would be great. But yeah. All right, so we've transitioned into the lab. I brought the power supply, well, the main transformer, this is just the power supply providing the negative and positive rails for the amplifier. And so I've just brought this section. I will say that the unit itself is a lot lighter without this transformer. This is with the bulk of the weight. I mean, this thing is huge. And so this is the power, the output of the amplifier with the power transistors. And then, of course, you have the preamp board right here that is socketed into this board. Now, all these transistors appear to be short. Um, some across all pins, some not, but I think all of these are gone. I've actually disconnected the negative and positive rails and the common um, lead as well. And basically what I want to do is check the state of this, this power supply here. And these two 10 amp fuses are gone. They're blown. So this, whatever happened here really is quite a short, and I'm sure these fuses are why it doesn't look a lot worse. you know, we don't see any visual damage, but anyway, yeah, so that's what I'm going to do. What I'd like to do is hook this up to an electronic load and really put these caps through a little juice through them to see if that changes anything. So we can do that as well. But just so we can roll this out, and then we'll go from there. One other thing, real quick. I'm almost wondering if it's clear that the original owner, the owner before the owner that gave this to me to repair, tried replacing these transistors. You can see they're a different package. These being the original, I'm assuming. But notice you got NPNs here up to here, and then you've got a PNP here, NPN, and then PNP again. I'm almost wondering if he flip-flopped these by accident and caused another short when he popped them in. But who knows? I'll have to trace this out a little bit to be sure. Okay, I think I have this right now. Just had to figure out how the voltage selector switch, main switch on the back, works. Because I can't just plug into the mains input, because that moves on to the rest of the unit, which we don't have with us. So we have to tap in via directly at the transformer. We just have to figure out what winding we want at 110 volts or so. All right, so let's fire this thing up, see if we can get it to work. Okay, and we have our negative rail at roughly 37 volts. Okay, that's to be expected. I think it's 36.5 in the schematic, but and we can check. Let's try to check our positive rail. And we have that too. Okay. Yeah. Well, there you go. I think what we can do now, though, is just hook it up to a load and see if it does anything strange, but power supply looks good so far. Yeah, so I don't think our caps, well, there's no ripple, right? We're AC coupled right now. I mean, so we got a really clean signal, and that's the negative rail. We can try the yeah. So yeah, I think we can just real quick hook it up to a load, see how it performs, but I think the power supply isn't the issue. All right, so we're hooked up to the load. Let's see what happens when we Alright, so we're at 1 amp. That's a good sign. Alright, so now it's on to finding where the short is on this board. But before we get into that, these transistors, he's definitely got these flopped around, the original owner. These should all be PNP on this side, NPN on that side. And I can even show you, because all the bases for the large power transistors are tied together, right? Base, collector, emitter, that's how these are 1, 2, 3. And so this trace goes, snakes around here, comes up here, goes to this base, right? And then it connects to the emitter for this guy. And then you've got this connector here, which is this jumper here, which ties into the final base right there. So, yeah. And so that definitely would have been an issue if you tried to fire this up. You know, so that's that's a problem right there. But what caused the initial fault, I'm not sure yet. We'll have to figure that out. But I think we'll start popping these transistors out and testing them. We can have some fun with the curve tracer maybe. Yeah. Alright, so I removed the power transistors from the output amplifier board, and believe it or not, it appears that some of them survived this debacle. And yes, whoever tried to repair this definitely swapped one pair of the NPN and PNP transistors, which probably caused it to blow again immediately. Doesn't explain why it happened the first time, but anyway, let's take a look. So these are our NPN transistors, and you've got base, collector, emitter. So this guy looks like it could be good. This one, nope. Completely shorted. And then we got this guy, who also appears to be good. Interesting. So it appears that 2 of the 3 NPN transistors made it out alive. And so these are our PNP. Alright, this one looks good. That looks funky. Yeah. I don't think this one's okay. And then finally, yeah, this guy's no good. Alright, so 2 out of the 3 NPN transistors appear okay. 2 out of 3 PNPs, no good. Alright, so we got the amplifier section of this mixer. It looks like a rat's nest going on here, and you know, I got a few things to go over about what I found wrong with this thing, but we're going to go over that later. And I just wanted to go over just checking the DC offset and then the DC bias. So starting with DC offset, the manual states it should be plus or minus 20 millivolts, and I've allowed this thing to heat up for a little bit, and you can see we're doing just fine there. You're checking this with no load, although that load resistor there is not attached. And we've got this thing hooked up to my isolation transformer and my power meter, and we're connecting there at the transformer. And yeah, so so anyway, we got our DC offset looks good. So I think now I'll show you the DC, the bias, the quiescent point adjustment. All right. So the manual is in German, by the way, and I did find a service manual online for an Eminent 100A, which looks to me just has only 6 channels, not as much power output, but relatively the schematic is pretty much the same. Um, and so therefore the instructions or service procedures are going to be a bit similar. So uh, found that and found the DC offset. DC offset's pretty straightforward for any amplifier, but for setting the bias, that can differ between amplifiers, especially because I don't do these all that often. So the bias current, or what we're trying to set, is the quiescent current. So the current that is drawn with no signal applied, and you're setting that so that it is just enough to get a symmetric signal from positive to negative, and also to help with crossover distortion. So the manual has you setting, it doesn't specify to attach a load, but you normally would to do a bias adjustment. And it says just output of 250 250 millivolts at 10 kilohertz, and keep the bias pot all the way down, and then slowly bring it up until you start to see a knee in the sine wave disappear, or you can kind of see. So right now I'm just injecting the lowest amount of signal that I can, which is 10 millivolts, and that's giving us an output, an RMS of roughly 1.3 volts. All right, and this guy's bouncing off all around. It's because there's just some 60 hertz noise that is riding this signal. But if you look here, oops, sorry, you can see these notches. So you can see a little bit of crossover distortion going on here. And what we're going to do is just bring this pot up. Basically, we can look at the schematic a bit, but the way they've got this bias circuit set up is you've got this transistor that's driving, that's acting basically as an adjustable diode, and it's giving us a voltage drop range between 2.8 volts at the lowest setting and like 3.5 volts at the highest. So we're going to bring, and I have a meter across it now, we're reading 2.8 volts across the collector to emitter. And we're just going to start to bring this guy up, and you guys can see what's happening on the scope. You can just about see we've made that notch go away. Right? Might have had it a little bit better, actually. It's hard to tell with this signal being so noisy, but yeah, no. That looks a lot smoother. Yeah, that looks a lot better. All right, and so that's how you would set the bias for these types of mixers. All right, so we are practically taking this guy up to almost the max output. For a sine wave, it's going to be a little bit lower, but we're at 105 watts, 1.3 amps, and we have a really nice looking sine wave there. Nice and clean. One thing that is a little concerning, though, and I don't have this hooked up currently, but I was looking at this a bit, is that the negative rail draws a lot more current than the positive rail. and it's almost up to like 600 milliamps more. And that could just be intrinsic of the circuit. I'm not too sure, but yeah, that's one thing I noticed. I mean, clearly we have it biased properly. The DC offset is set correctly. But, you know, it just leaves me feeling a bit uneasy, that large difference between the two. But it could be the way it's supposed to be. I have no idea. Um, but yeah, so there we go. I'm going to disable this and we can kind of go over the, you know, what else I found on this guy that needed repair. Alright, so now that we got the bias adjust and the DC offset adjust out of the way, I do want to go over what I did to get this thing into a working state. At least so far, so good. But so obviously, yeah, I replaced all of the power transistors. I was able to get the originals, those BD 245s and 246s from a seller on eBay. Seller in the US seemed like a reputable seller. They came in pretty quickly, tested them on the curve tracer, they all looked great, and so popped those in. But there were a couple other things going on this amplifier that needed addressing, and one of those was actually quite interesting. So if you look here at that little solder bridge there, right here, so this connection is supposed to be there, and some of these connections are just, you know, connected via a glob of solder and not necessarily a copper trace. I'm not sure which this was originally, but there was no continuity between those points. Okay, so this is that point on the circuit board where that solder bridge or copper trace got disconnected in between diodes D407 and D408. And so what was happening before I discovered this is I replaced all the power transistors, powered the thing on using my benchtop power supply just to be, you know, so I could control the current, and the current shot way up. The voltage rails were dropped, and this resistor R410, this 240 ohm resistor, it started smoking and getting very hot. And so this is a pretty typical current source being biased with these two diodes and this resistor. And so when this thing is working properly, you've got roughly one diode drop across this resistor. So this current source is able to provide about 2.5 milliamps of current to the load. With this diode, these two diodes being disconnected, this transistor is no longer being biased properly. The voltage across this resistor is going to shoot up, and the current is going to increase by an order of magnitude. And with this being the current source for your bias network for the power transistors, that's going to have a huge problem, or could potentially cause huge problems downstream. It could cause your transistor to go into thermal runaway. So this could be what was causing the first failure to occur. This could explain why it blew the power transistors in the first place. It definitely could cause that. But anyway, and you know, we can show you guys an example of how this would work. I basically just built a little current source here on a breadboard. So you've got your PNP transistors, and this is just being biased with an LED. You could use that as well instead of a series of diodes. And if we power this guy on, watch the current draw. It's very low right now at 0.01 milliamps. And we can even take some measurements at the emitter, at the emitter, base, and collector. That's not going to work, right? Okay. So here we are, 15.8, 15.9 volts. We're providing a random 17.2 volts on the positive rail. But so there you go. You've got your, let's see, so you've got there's going to be roughly 1.8 volts across this LED, and so you subtract 0.6 and you've got roughly 1.2 across this resistor, right? Or 1.3. Okay, watch what happens if I remove this LED. See if I can. You see that current shot up? So it was basically at 5 milliamps, which is why this was rounding up to 10. But as you can see, we are now at 70 milliamps. So you can see this thing almost shot up over an order of magnitude, and that's what it would have occurred on the the amplifier. And you can see now the voltage across this resistor is now 15 volts instead of a nice 1.3 volts, and it's getting very hot. So that's what happened on this amplifier board, and I'm hoping that appears to be the culprit that caused the initial failure, and that we've got it fixed and we can just move on and get this thing finished. So there was another thing that was wrong with this guy as well, and that was the DC offset pot. So it was originally one of those wheel type pots, which one of these guys, and there was just way too much play in the wiper, and it just wasn't making contact. This is a 5K pot, and it was just really acting as a 5K resistor. So I did replace that with a 10K trim pot, hence the 10K resistor that is across it to make it a 5K pot. Those were the two main things. I did recap the electrolytics on the preamplifier board. That's just what I've been calling it. Yeah, so with this done, at least it appears to be done, what I'd like to do now is start focusing on some of the other boards, recap the other power supply board, and there is another amplifier board for the monitor that's a little different, and then I've already cleaned all of the faders and pots throughout the rest of the unit, and but yeah, you can kind of move on from here. Okay, so we recapped the other power supply board that's just hanging here haphazardly. Yeah. Anyway, so we're at 36, a little over 36.5 volts. And if we AC couple this, we have a really clean signal, very little ripple, so I'm not too worried about that. Yeah. So there you have it. That board should be ready to go. And I also recapped this monitor amplifier board as well, so we can check that. But look at the caps that were in this thing. I mean, they are so pretty. You could like might hang on to these, turn them into a Christmas ornament or something. Yeah, really cool. And just a quick overview of this power supply that we just recapped. This is being a bridge rectifier is rectifying this from a separate winding, and these are the two large caps in parallel, 1000 main filter caps. Got your series pass transistor here that's being driven by this transistor. This is your current limiting transistor here, which will sink current away from the driver transistor when this guy turns on. The current gets too high, shutting this guy off. And then you have this transistor here, which is involved in the feedback circuit to adjust your output voltage. With you have this 6.2 volt center that's involved in that as well. Yeah, pretty simple, and it's working just as it should. Okay, so this is the monitor amplifier, and we've got a 4 ohm load hooked up to it, and we are basically driving it to the max, although you can see it's clipping. It's starting to clip on the lower end of the sine wave before the positive peak. It's drawing almost 1 amp right now. And but yeah, it is working, and we are inputting a sine wave of 500 millivolts amplitude, and this guy should be able to do a maximum sine wave of 9 volts RMS, and we're just about there. Alright, so we are back at home, all back together. The rest of it came together quite smoothly, and it moved pretty quickly after that, so I didn't really have much to share. And as I hoped, the magnetic tape delay, I didn't have to do anything with it. It works perfectly. So I've already given it a little bit of a test. I am going to show you guys a demo of it in action. Yeah, so just a couple things to note. I mean, if you guys remember, this input number 3, channel 3, the fader for the volume control, the shaft had broken off, and so I did replace that. This is the original, and you can see that shaft is just broken right at the base. Now these are an interesting, well, a unique range of motion of 70 millimeters. You're not gonna find anything like that on Mauser and DigiKey. And so I was able to find one on eBay that had that 70 millimeter range and then 80 millimeter mounting length, which is what these are. These are 25K. The replacement I found was 50K, so I just put a 50K resistor across it. It is a bit hotter than the other channels, so I'm going to make a note of that to the end user, but it works. Yeah, and I mean, I cleaned all the faders, all the pots. You know, this, if you guys remember, the top panel, it was missing when it came in, so unfortunately we don't have that, and that kind of is a shame because that's the most delicate piece of the unit, it being exposed there. But I mean, it works, and it sounds great, and so I'm really excited to show you guys it in action. So let's do it.